This is the inductor you've spent 3 years in school not fully understanding. In fact, its working principle is quite simple. First, we know that when current flows through a wire, a magnetic field is generated around the conductor. The larger the current, the stronger the magnetic field. This is Ampere's law. If you weren't dozing off in class back then, you'd also remember that the direction of the magnetic field can be determined using the right-hand rule. If your right-hand thumb points in the direction of the current, the other 4 fingers point in the direction of the magnetic field. Now, if we coil the wire into a loop, the magnetic field becomes more concentrated, creating a stronger magnetic field that closely resembles the field of a permanent magnet. This is the most basic form of an inductor. By increasing the number of turns in the coil, we can strengthen the coil's magnetic flux. We can also vary the magnetic flux by changing the amount of current flowing through the coil. On the flip side, according to Faraday's law of electromagnetic induction, if the magnetic flux in a coil changes, it will induce a voltage in the coil, which in turn produces a current in the circuit. Here's where it gets interesting. A changing magnetic field induces a current in the coil, and the current itself produces a magnetic field. So what happens when a coil is placed in a closed circuit and the current changes? That's where Lenz's law comes in, an extension of Faraday's law, which states that if the current changes, a reverse voltage is induced in the coil of the inductor to oppose this change, thereby resisting the variation in current. This is known as the phenomenon of self-induction. Let's look at a simple example. If an inductor is connected in parallel between a light bulb and a battery, you'll notice something fascinating. When the circuit is closed, the light bulb lights up first, but then turns off after a moment. And when you break the circuit, the bulb lights up again briefly before turning off once more. Let's slow it down to see what's happening. When the circuit is first closed, the current flows to the light bulb first, because the magnetic field in the inductor is still building up. As the magnetic field strengthens, the inductor generates a back electromotive force, back EMF, through electromagnetic induction. This back EMF opposes the battery's voltage, thus resisting the increase in current and reducing the current flowing into the inductor. As a result, more current flows into the bulb, lighting it up. Over time, the magnetic field in the inductor builds up until it reaches its maximum. At this point, the inductor's resistance becomes almost zero. It acts like a plain wire. The current bypasses the bulb and flows directly through the inductor, causing the bulb to go out. Now, if you disconnect the circuit, the current flow stops, and the magnetic field inside the inductor starts to decay. This decay again generates a back EMF that tries to keep the current flowing. The remaining current flows into the bulb, causing it to light up briefly once again. In fact, this is quite similar to how a capacitor works. Both are devices that temporarily store energy. However, an inductor stores magnetic energy. When powered, energy is stored in its magnetic field, and when power is cut, that magnetic energy is released and converted back into electrical energy for the circuit. An inductor's ability to store magnetic energy depends on factors like the number of turns in the coil, the length of the coil, the cross-sectional area and perimeter of each coil turn, and the permeability of the core material. Inductors are very useful in circuits. For example, when combined with capacitors, they form filters that can remove noise from electrical signals. They're used in switching power supplies to stabilize output voltage. In wireless charging devices, they can interact with another coil through mutual inductance to wirelessly transmit energy. Even in audio systems, TVs, computers, and automotive electronics, inductors play important roles.